So in this video clip, I'm going to take a look at predicting wine quality in our Studio Cloud. So we're going to take some data, a very simple data set that's available in MIT OpenCourseWare. And that data is based on a paper, fairly old paper going back to the 1990s, authored by Arlie Ashenfelter, who was an economist at Princeton, and he had some expertise in wine and an interest in wine, and he brought a number of statistical techniques that he thought would be useful in terms of predicting wine quality and wine price. The paper was quite controversial. It upset the wine elite at the time. He felt that there was a variation in quality and price from year to year that can often be quite significant. Orley noted that there were quality differences had been depicted in the trade as a great mystery. And he demonstrated that if we want to predict the price of wine, and there is some skill associated with that, some factors relating to the weather and temperature, rainfall at different periods contribute to the quality and ultimately the price of the wine. And this was a kind of, at the time, this was regarded as a form of heresy. Now, to get some additional context here, it's worthwhile having a look at this video clip from ABC, Good Morning America, and there is some useful context that you might take a look at. But basically the problem, if you like, is that, and he described the objective of the paper. When a red Bordeaux wine is young, it's astringent, and most people find it unpleasant to drink. As the wine ages, it loses its astringency. Because Bordeaux wine tastes better when they are older, there's an obvious incentive to store them until they have come of age. As a result, there's an active market for both younger and older wines. Traditionally, what has not been so obvious is exactly how good a wine will be when it matures. The ambiguity leaves room for speculation, and as a result, the price of the wine when it is first offered in its youth will often not match the price of wine when it matures. So there's some kind of market inefficiency here. The primary goal of this paper is to study how the price of mature wines may be predicted from data available when the grapes are picked, and then to explore the effect that this has on the initial and final prices of the wines. The secondary goal is to show how this straightforward hedonic method has now been used in many other grape growing regions to quantify the role weather plays in determining the quality of wine vintages. So the idea was quite simple and disarmingly simple, so much so that it obviously evoked a very strong reaction from people in the trade. So what we're basically going to do is try to replicate the Ashenfelter results, and we turn to MIT OpenCourseWare, and they have provided, in fact, if we go to the course homepage here, they have a module here on data analytics. It's very comprehensive. There's a lot of detail. They describe many of the more practical techniques like linear regression, like logistic regression, trees, decision trees, text analytics, clustering, visualization, linear optimization, and so on. So there's a lot in here, and one of the areas they address is linear regression, and each segment that they develop here tends to come with a video, some explanation. So what I'm going to do in this video is just say, okay, take it, just back it up one step and say, if we have the code, and I take the code, from the MIT OpenCourseWare. How do I set that up in RStudio and then load in the data? So that's really our main problem here. And okay, in the next few steps, I'll demonstrate how we can undertake that. Okay, so what I'm basically going to do here is just show you, normally when you go on to RStudio Cloud, you load that in, it'll bring you to, brings me directly because I'm signed in. I'm going to sign out for a moment, and if you go into RStudio Cloud, you either log in or sign up. If this is your first time, you have to sign up. And that means you set up an email address, you put in your password, give your name, and then you might link it in with either a Google account or GitHub. So I'm going to pause here and enter my details and log in. And then what we'll do is we'll go through the different steps required to set up the estimation for linear regression. So I've logged in here and I'm in my workspace. So to set up a new project, we'll just go new project. That might take a second. There is some latency, so it's wise perhaps to pause again. Okay, so we've set up a new project. We better give it a name, and just to make clear that it's coming from MIT OpenCourseWare, maybe we'll make that explicit, right? MIT OpenCourseWare. And of course it's wine quality, right? So we're trying to predict wine quality, and we're replicating Ashenfelter study in his paper, right? So so basically we have here a blank canvas, we have no data, and we have no code to run the project. To get the code, I'm taking it from, you'll find the code at this web address, that HTML address. So we'll just copy here, copy, then go back into RStudio, and we need to load in the code. So we'll create a new file, and it's an R script, and then we paste, right? And at this point, it might make sense to save, and it should prompt some name. So it's wine quality and MIT, right? So that's the name of this this file, right? And we'll just save. Okay. So next thing, we need data. And as it turns out, there's a couple of ways I can get the data, but just to be consistent here with the analysis, I'm going to take the data directly available in the MIT OpenCourseWare section 2.2.7, and this is consistent. This data is the original data from the paper, and there's only a number of observations, so we need to download those, and they've gone into the downloads. Then I go back to the RStudio environment, and I must upload, right? So we need to upload those two files. Okay, so we have to choose a file, and we'll go into downloads, and it's the two most recent. So let's take wine test, open, and it appears, and then likewise again, upload, choose file, and wine, which is the larger data sets, but only a small number of okay, so we click OK, and it's gone in. Next thing, we need to put this in our global environment so that we can call it into to execute these commands on the data, right? So at the moment, if I run the script here, it'll just create a whole range of errors, okay? So I need to load this in. Now it's easy to load in. We just say import data set and say yes. Okay, and it's loading. So maybe I'll pause. And we can see the data. This window now has opened up, and we can see our data appears here, and this command then is executed, right? So we'll just say import. Okay, and now it appears, and it's fairly clear. It's really a minuscule data set. Next, we want to import data set for CSV, and you can see there's no more than basically 26 or 27 observations here. Okay, so a small data set with the year of the wine, the average price, but a logarithm of of an averaged price of a particular wine, the level of precipitation, so winter rain, the average growing season temperature in Celsius, the harvest rain, which is generally the higher harvest rain, tends not to help the wine. The age of the wine, Bordeaux wines become better with age, and then population of France. So let's just import. And we now have that there. And I did have to make a couple of small minor changes in some of the syntax here, and that just related to the naming of the files. So to make consistent between what I got from the MIT OpenCourseWare portal and what actually were the true file names, some minor adjustments. Okay, if you want to track back the origins, there's a handy HTML here. So let's just have a look then at the structure of the data. And when we look at the wine data, as we saw in the RStudio viewer, year, price, winter rain, average growing season, temperature, harvest rain, age, population in thousands, right? So then maybe a summary that gives us first quartile, third quartile, mean, median, and you know the first wine was 1952, the latest wine was 1978, and the price here is not in French francs or I think it's in US dollars, but we take the logarithm. Sometimes we take the logarithm to linearize the data, and that avoids some problems. Winter rain, average growing season temperature, minimum and maximums, harvest rain, age of the wine, and then population, right? So they're to break down the basic descriptive statistics. Now, when you're modeling, we want to run perhaps a regression. Obviously, a good place to look at the background to estimating is run through the video clips here. Also, if you go to the portal, and go to useful concepts and then introduction to linear regression here, I have fairly exhaustive set of video clips explaining the residual sum of squares, total sum of squares, explain sum of squares, and I do a lot of this analysis in Excel, so it's a little bit visual with a relatively small data set. So that's available. Okay, let's go back to predicting wine quality and to our RStudio environment, cloud environment, and we run the models, right? So the first model is a linear regression model where we use the average growing season temperature, and we use that to predict the price, right? And we get summary of the output, and the output we have is the intercept and the coefficient. They're both the coefficient on the average growing season temperature is statistically significant. The p-value is really small, and interestingly, the R-squared here is 43%, and the adjusted R-squared 41. So not bad, right? And so temperature seems to be important, right? First point. And standard types of metrics we would look at here are some of the square errors. I explained that in the same portal. The lower this number is, evidently the better, right? But we do need to scale it for the number in the sample. So if the sample size is small, then it's not a surprise that the sum of the squared errors is small as well. So may not be that revealing. What's most revealing, possibly in this instance, to compare one model against the other, is really to look at the R-squared, right? Okay. Then in our model, we say, okay, let's try to predict the price using the average growing season temperature and the harvest rain, and then get an output or a summary of the model. And again, we find that when we introduce that second variable that includes the harvest rain, we get an R-squared of 68%, an adjusted R-squared. So we've improved quite dramatically the explanatory power of the model. And also here, a couple of interesting things, I suppose. The higher the temperature, it would appear, the higher the price, and thus higher the quality of the wine. And that's statistically significant because the p-value is less than 0.05. And then harvest rain is negatively related to the quality and the price of the wine, right? And that's also statistically significant, and the p-value is less than 0.05. So there's a positive relationship between temperature, average growing season temperature, and the price of wine, and a negative relationship between harvest rain. So that's rain when the grapes are picked. Okay. And again, we can do some of the square estimation, and we find it goes down. We then take a look at this next model, and it's just we're adding on an extra couple of explanatory variables. So now we're going to have winter rain, age of the wine, and then the population in France. Could be a proxy for something. And let's look at the output here. And what we find, again, positive relationship between the average growing season temperature, negative relationship with the harvest rain. Winter rain, there's a positive relationship, and that's not quite statistically significant. And the age has a low t-value, so we can't say that it's statistically significant. And then the French population, something going on, not statistically significant. And maybe this is not helping us here. And maybe there's something, some interaction between the two. So we might want to refine our model. You can look at the sum of the squared errors. That's down to 1.73. That's great. Mainly the R-squared we're interested in. It's 78%, and that's not bad, right? Then and of course this is in sample, we refine our model bit. We exclude the French population. We leave in age, and we leave in winter rainfall and harvest rainfall. Now when we look at these variables, we see something interesting. Again, the same positive relationship as before with average growing season temperature. Harvest rain is negatively related, both statistically significant. Winter rain is also statistically significant, and it's positively related to the price of wine. Harvest rain is negatively related, and then the age of the wine is positively related to the price of the wine. So the older the wine, the intuition that the older the wine, the better the wine, we seem to be able to justify that, and we have a p-value less than 0.05. So it's definitely statistically significant. That's an important result. Now, more globally, we can do some correlations here and compare winter rain and price. and it's positive. So we've correlations, and then the age of the wine and the French population, that's strongly negative. So obviously one was affecting the other when both variables were included in the regression. One was cancelling the other, but population mightn't serve maybe just a time marker in France, and that's how it's maybe corrupting a little bit the relationship. Age is generally considered an important factor in determining the value of the wine. The correlation of the wine, then we could run a correlation coefficient. Let's run that. A correlation matrix, should I say. And again, for some understanding of the correlation matrix and the covariance matrix, you might just take a look at the useful statistical concepts and take a look here at the variance covariance. It's a fairly standard type matrix that's used in many different areas of science, business, marketing, but also in finance. And the example that I gave here is in finance. Okay, so let's go back into RStudio for a moment. And interestingly here we find that, of course, on the diagonal, it's always 1. And then off diagonal, the price in year, again, it's probably easier to express this as age. There's a positive correlation between price and age, right? That number is the same as this one. They're identical, just this is negative. So we can understand that the year of the wine and the age, obviously, are one of the same thing. It's two sides of the same coin. We might look at price and winter rain. There's a positive correlation. Price and average growing season temperature, positive relationship. Price and harvest rain, negative correlation. Price and age, positive correlation. And price and French population, this looks like a time marker of some kind. So it might be proxying, but could be if the population is growing and wine production wasn't, that would push up the price of wine, and French population was growing over time. But that analysis is not straightforward here. Okay, so let's remove age and the population, and this is model 5. We take a look at the R-squared 71, right? Okay, so they're interesting. Of the 4 models, maybe model 4 has something to offer here. Let's just continue with the analysis now. So far, we've been looking at the R-squared and judging the performance of the model with in-sample R-squares. It may be more important that we can prove our model is good. And one way of doing that is going out of sample and then predict. So we use model 4 and the wine test data. Now the wine, if we look at this structure here, this table, you can see it's for 1979 and 1980. And we just have 2 observations. So if we come over to wine tests, you can see it's a very limited data set. But we want to predict, using our model, we want to predict these 2 observations that were outside the sample, right? So we go back here and we predict, and we're using model 4, keeping in mind that model 4 had average growing season temperature, harvest rain, winter rain, and age only, and we excluded the French population. So let's run that, and then we'll predict test. We get the output. And what this says is for the first, for I think 1979, we're predicting that the price of the wine in logarithms is 676. And for 1980, it's 686. And when we compare that against the true values, it's not that far off. Right? You can see comparing this against this, quite close. And likewise, using Ashenfelter's model, they're quite similar. So this is not a bad model for predicting the price of wine. Now, how would we judge how good the performance is? Well, you could eyeball it just the way we did, or we could perform an R test, an out of sample R squared, and the out of sample is 79%, and that's really good. The only reservation I would have here is that this is such a small sample, right? The sample size is too small. Okay, now for more in-depth treatment of this area and background of the statistical measures that we use here, first port of call, MIT OpenCourseWare. Second port of call, you might come here to the introduction to linear regression and take a look at that, the outline here, right? Some of the basic concepts I go through painstakingly, okay? Okay, so let's leave the analysis there.